introducing Dr. Claire Parkinson, who's a climate change scientist at the NASA Goddard Institute for Space Studies. Her research emphasis is on sea ice and climate change. She's used satellite data to reveal long-term trends in the sea ice covers of the Arctic and Antarctic, and has also done computer modeling of the sea ice covers and field work in both regions. In addition, since 1993, she's been the project scientist for the Earth-observing Aqua Satellite, which launched in May 2002 and is collecting data on many atmospheric, ocean, land, and ice variables. Claire is a member of the National Academy of Sciences, National Academy of Engineering, the American Philosophical Society, and she's a fellow of both the AAAS and the American Meteorological Society. We're very fortunate to have Claire giving a talk which is entitled Polar Sea Ice Coverage, Its Changes, and Its Broader Climate Impacts. Claire, thanks very much for coming.
David, thank you. Thank you. And due to Dan, I finally got a copy of the book last week, so I'm extremely pleased to finally have a copy of the book. And it looks great, except I did expect and wanted some picture in the front. You know, I wanted to open it up and see David's picture right there with the dedication to David, but I realized maybe there were NASA rules or regulations that didn't allow that or something. But anyway, the book looks great. Okay, Dan, next slide. Okay, I realize that most of you probably are well aware of what sea ice is, but for those who might not be, sea ice is ice that was formed by the freezing of seawater. So it's different from icebergs, which also are ice that's floating in the ocean, but came from land ice instead of sea ice. So, sea ice is a little salty. It's not as salty as seawater, but it does retain some of the salt from seawater. It's way, way, way thinner than icebergs tend to be. So if sea ice is 5 meters thick, that's thick for sea ice, whereas that would be very, very thin for an iceberg. So there's a big difference between sea ice and icebergs. Next. This shows the extent of sea ice kind of in a typical March and a typical September. I'm using the slides here, the exact same ones that are in the book, so that those and that are on the website, so that I'm speaking directly to them, although I do have numbers in front of me that will allow me to update some of the numbers through to the end of last December, so through to the end of 2018. So sea ice tends to extend out to its maximum extent in March, and at that point it tends to be about 15 million square kilometers. This is roughly 1.5 times the area of the United States. So it's a very large area, and surely it would be extremely difficult to get a routine measurement of the entire coverage of sea ice without having satellites. If you think of how could you get routine measurements around the entire United States by either aircraft or land measurements, it would be very difficult if you didn't have people in many cities around the US and you don't have people living on the sea ice other than for very brief periods. So huge area of sea ice in the wintertime at its maximum. It goes down quite a bit in summertime, so that in summertime, the mean for the period from 1979 to 2014, and why that period's picked will become clear in, soon, is 6.3 million square kilometers. If we update that to today, adding in the last 4 years, it's still pretty close to that. It's 6.2, so it's a little bit less, but still pretty close. Now, these images are made from satellite data, and satellite data basically are the only data that we've got now that really could give you a really good picture day after day after day, year after year. And the reason that I start here with 1979 is that a major satellite was launched in October of 1978. Near the end of October 1978, it had an instrument on board that is the type of instrument that we've been using ever since then. It's called passive microwave, and the microwave simply means that it's measuring in the microwave region of the electromagnetic spectrum, and passive means it's not sending a signal down and receiving it back like an active instrument would do, like a laser or a radar, which sends a signal and receives it back. In this case, it's just receiving. It is not sending something down and receiving it back. So it's a passive microwave instrument, and huge, huge, huge plus of the passive microwave data is that it allows us to get the sea ice coverage day after day after day, irrespective of whether it's summer or winter, whether it's dark out or light out, because the microwave data are coming from within the Earth system. They're not coming from the sun. So since it's from within the Earth system, it really doesn't matter whether there's sunlight or not. And also, another huge advantage of the microwave data is that at selected regions in the microwave, the data actually, the radiation actually can go through most cloud covers. So therefore, it doesn't even matter if there are clouds there. And that's a very cool aspect in terms of the satellite is able to see through the clouds to the surface underneath. So it's those data, the passive microwave data, that are the basis of the data that I'll be showing. I'll also be showing some modeling results, but the data are coming from these passive microwave instruments. So next. This shows the corresponding images for the Southern Hemisphere. In the Southern Hemisphere also, there's a huge contrast between summer and winter. In fact, the contrast is even larger than in the Northern Hemisphere in terms of how much sea ice there is. So in the Southern Hemisphere, in the summertime, which because it's the Southern Hemisphere and therefore the seasons are reversed, its minimum ends up being in February, and the average extent ends up being about 3.1 million square kilometers. And that remains the same when we add in the next 4 years, other words, through the end of 2018. And then it expands out, and it expands out to its maximum in September. And at that point, the coverage is roughly 18.6 million square kilometers. So much bigger difference between summer and winter. And if you look at the geography here, you can understand why. In the Southern Hemisphere, as pictured in this slide, you can see that the ice can keep expanding outward in wintertime because there are no continents that are kind of restricting it like there are in the Northern Hemisphere, where you've got the ice reaching out to North America, Europe, Greenland, Asia. And so its wintertime extent is very much confined in the Northern Hemisphere, but it's not in the Southern Hemisphere. And then in the reverse, in the summertime, you can see by the geography that the continent of Antarctica, which is in gray in this picture, the continent is in the high latitude regions. So that portion of the highest latitude regions, of course, doesn't have sea ice because it's got land ice instead. Whereas in the Arctic case, the central portion of the the polar region is an ocean instead, the Arctic Ocean, and so that retains a larger amount of ice than the southern hemisphere does in the wintertime, in the summertime. So on the right-hand image, the update of that number, 18.6, when we add the next 4 years in, it becomes 18.5. So not a whole lot of difference. Next. Okay, so sea ice extends over a huge area, and so therefore you might wonder, well, does it really make any difference whether you've got sea ice or not? And it does make a lot of difference. And this slide is kind of illustrative of the kinds of differences the sea ice makes in the polar regions. First of all, sea ice is highly reflective. So most of the sun's radiation that comes down and strikes the ice bounces back, reflects back, goes back out to outer space. Whereas if the ice isn't there, most of the radiation that strikes the liquid water surface of the ocean goes into the ocean, stays within the Earth atmosphere system, and helps to warm it up. So that's one huge impact of the ice. It reflects solar radiation. Another huge impact is that it restricts heat fluxes from the ocean to the atmosphere, or if the atmosphere happens to be warmer than the ocean, then it restricts the heat flux from the atmosphere to the ocean. So it serves essentially as an insulator between the atmosphere and the oceans. And then other impacts are that as ice forms, some of the salt content of the seawater drops out, making the water exact right underneath the ice a little saltier, which sometimes will mean denser. And then if it's dense enough, it can result in overturning of the waters underneath. And this happens not only while the ice is forming, but also as it ages, more and more of the salt will tend to drop out. So that's another huge impact that the ice has. Next. Okay, now, therefore, with the fact that it spreads over a large area and has impacts, David led a study, and I was extremely pleased to be a member of this study, and Doug Martinson was too, and Rick Healy. So the four of us did this study led by David, and this was a really neat study in terms of being very clean cut, using a model to figure out how much impact does the sea ice have on what happens to the atmosphere temperatures in the event of a doubling of CO2. So on this plot on the left, the red curve shows the impact of doubling CO2 in the GISS climate model if running it the normal way with sea ice calculations being done. So the x-axis shows latitude. So we're at the South Pole at the left, and the North Pole at the right, and the equator in the middle. So you can see that if using sea ice calculations and running the model, no matter what latitude you're at, you're getting warmer temperatures in the event of a doubling of CO2. And the temperatures tend to be warmest in the regions, the warming tends to be highest in the regions of the sea ice cover in the polar regions. Now, look what happens if in this model you remove the calculation of sea ice. So we still had a seasonal cycle of sea ice, but we had the exact same seasonal cycle every single year. And the model did not calculate sea ice. So as warming occurred, sea ice was not affected. It stayed the same annual cycle. And the blue curve shows what the temperature effect then was. And this is pretty remarkable in terms of that's all we did with the difference between the two sets of GISS climate model runs. One included sea ice calculations, the other didn't. And the warming ended up being affected at every single latitude. It's not just the warming in the polar regions, but every single latitude, the warming was less if you didn't allow the sea ice calculations to be included. So the results here show that the warming simulated for globally, so if you take it, you integrate over the latitude, the warming simulated globally was 4.17 Kelvin with the red curve, so with sea ice included, 4.17 Kelvin. If you remove the sea ice, so the blue curve, remove the sea ice calculations, the blue curve, it's down at 2.61 Kelvin. So that's a reduction of 37%, 37% just because of the sea ice effect. So again, this was a study done by David, led by David, and a really clean result. Now, of course, it doesn't mean that that's what would happen in the real world, but it does mean that's what happens in the state-of-the-art GISS model at that time of the publication, which was back in 1995. And great project to be a part of. And as I said, I was really pleased to get to work with David and Doug and Rick on that. Now, the right-hand picture here shows an illustration that shows temperatures from satellite imager, the atmospheric infrared sounder on the Aqua Satellite. So it's satellite data showing this tongue of cold air coming down and causing very cold temperatures. And this happened to be for February 19th of 2015. But you have similar pictures for this past January where the cold air is coming down. Now, some people say that these excursions of the cold air south could be in part due to the sea ice, changes in the sea ice cover. Now, you would get these kinds of excursions in the past also, but the issue is maybe they're more frequent or more intense because of changes in the sea ice. And one of the people who's kind of most noted for looking into effects of the sea ice changes on mid-latitude weather would be Jennifer Francis at Rutgers. So her papers would be ones to look at for those who might be interested in this type of possible connection there. So next. Okay, this shows an artist's rendition of the Aqua Satellite, which has one of these instruments, passive microwave instruments on it. It happens to be an instrument that was provided to the Aqua Satellite. The Aqua Satellite is a NASA satellite, but the instrument here is a Japanese instrument. And that's illustrative of the fact that we at NASA do have lots of international collaborations, very important international collaborations. So this instrument was provided by the Japanese, and it did get the type of information that I'm showing in the satellite passive microwave record. that instrument is no longer working. It lasted far, far longer than its design lifetime, but it has been succeeded by another instrument of the Japanese on a Japanese satellite. So next. Okay, now we could start looking at this passive microwave satellite record and what it's showing. And this one shows the sea ice coverage month by month throughout this record, starting with the launch of the Nimbus 7 satellite back in October, late October of 1978. So the first data point here is for November of 1978, because that's the first full month of the record. And this plot goes through to the end of 2014. And by this point, you can tell, especially with the numbers in the summertime, you could tell that there's a downward trend. When we first started looking at trends, when we did the monthly plots, you really couldn't be sure whether it was downward or not, and we had to make adjustments. But by now, the downward trend is pretty clear, even with the monthly plots. But still, the monthly plots, basically, huge thing that's shown is that there's way more ice in the wintertime, peak almost always being in March, and way less in the summertime, where the lowest point almost always is in September. So next. What we do is to highlight the trend more. We remove that seasonal cycle that's so dominant when you look just at the monthly averages. And we do it two different ways. One would be simply average every day of the year and get a yearly average. And the bottom plot here shows the results for a yearly average. The other way that we do it, where we retain more of our data instead of just averaging the whole year, what we do is for that, well, for each month, we take that month's data and we subtract the average of the same month throughout the entire record. So January is only compared with the other Januaries. February is only compared with the other Februaries. And those we call monthly deviations. So you can see from these two plots that you've got a lot more data points when you do the monthly deviations. But whether you do monthly deviations or yearly averages, the trend is pretty close to the same. It's a strong negative trend of, in this case, negative 53,000 square kilometers per year with the monthly deviations, or 53,100 square kilometers per year with the yearly averages. Now, if we look at the extended record, if we add the next 4 years, then the updates are 54,700 square kilometer per year for the yearly averages and 54,600 square kilometers per year for the monthly deviations. So still very much a negative, and in fact a greater negative, and just for an indication of how much ice is being lost each year, it's roughly the combined area of Massachusetts and Vermont. So that's how much is being lost in terms of the areal extent of the Arctic sea ice each year. So next. Okay, this shows the trend for each month. So the months are on the x-axis, so January, February, March, etc. And then the y-axis shows what the trend is. And you could see that the trend, the biggest negative trend, so the bottom point here, the biggest negative trend, all the trends are negative. The biggest negative trend is in September, and the least negative trend is in May. And both of these are quite negative, but September is the most negative. And September continues to be the most negative if you add to the next 4 years after that. So next. Okay, this is another way of looking at the changes in the sea ice cover. So in the plots in the upper left, it shows how many days each of those 2 years that are plotted, 1978 and 2014, shows how many days of the year had sea ice coverage. Now, the big black circle in the middle shows that we didn't have data in that region. And if you notice in the 2014 case, there still is a black circle, but it's much, much smaller. Well, the contrast there is simply that in the 1979 case, we were using data from the Nimbus 7 satellite, which did not get any closer to the pole than what's shown with that circle. Whereas in the 2014 case, we were using a satellite that from the Department of Defense that actually gets a lot closer to the pole. So that's why there's that contrast there between the black circle in the middle. But in both cases, it indicates no data because of the orbit of the satellite. But if you look at those two plots, if you look at the sea that's the topmost sea in the plot, that happens to be the Sea of Okhotsk. It's right to the east of Russia. And if you look there, you can see a huge difference between the 2 years. There was much greater expanse of the ice in 1979 than in 2014. And if you look elsewhere and you try to compare those two, you could see that almost throughout the values of how long the sea ice was are higher, how long the sea ice season was are higher in the left case for 1979 than in the Dan, we seem to have gone off that image. Okay, thanks. What I did here was I took the record, the first 10 years of the record, and for every pixel, I calculated, or the computer calculated, but I calculated the trend in the length of the sea ice season for that 10-year period in the lower left image. And when I calculated that trend, you can see that in the Eastern Hemisphere, it's kind of dominated by the reds and the browns, which are the negative values, so shortening sea ice seasons. But in the Western Hemisphere, it's kind of dominated by it's got more of the greens and the blues, meaning that the sea ice season was lengthening. Well, then doing the same, but for the 20-year record up through 1998, and you've got that second picture on the bottom row, then it's much more dominated by the negative values. Then there's still some positives scattered around, but it's much more dominated by the negative. Then when you get to the rightmost picture up through the end of 2014, you can see that then it's pretty overwhelmingly dominated by the negative values, meaning the sea ice season is shortening. This is a big impact for like polar bears, because if the sea ice season shortens, they have to get out onto the land quicker and spend more time on the land. Now, that big area of blue on the rightmost picture, that's the Bering Sea. That's in between Russia and Alaska. When we extend that to the end of 2018, so we add the next 4 years onto that, that blue area is no longer there. So it continues to become even more convincing as a negative reduction in sea ice cover. So next. Now we turn to the Antarctic, and we do the exact same studies, types of studies in the Antarctic as we do in the Arctic. And now this time in the Antarctic case, with the monthly averages, well, it's still way, way, way less ice in the summer, which now is February because it's the Antarctic, the southern hemisphere, than in the wintertime where the peak is normally September. So in this picture though, it's not as obvious what the trend is when we look at the monthly averages. It's harder to tell than in the Arctic case where it was really pretty clear. So that's why it becomes really important to remove that seasonal cycle. So Dan, next. So now here's what happens when we remove the seasonal cycle. And now, instead of reductions in sea ice, it becomes clear that in the Antarctic case, there were increases in sea ice. So, and the trends are much less than in the Arctic case, where the trends were in the 50,000 plus square kilometers per year. Now it's down at like 22,000 square kilometers per year. But the important thing here is was increasing. However, in this case, when we add the next 4 years, there's been just a dramatic decrease in Antarctic sea ice coverage in the past 4 years. So it's still a positive trend overall, but it's overwhelmingly, if you look at the plots of sea ice coverage through the end of 2018, it becomes quite clear that these past 4 years have shown a huge decrease. And so if we take that and do the trend calculations on it, these trends of about 22,300 square kilometers per year, that gets reduced down to 11,300 square kilometers per year. So much, much less. And the last few years, as I said, have been really marked decreases in the sea ice coverage. Next. In the Antarctic, as in the Arctic, every single month shows the same sign of the trend. In the Arctic case, every month showed negatives. In the Antarctic case, up through 2014, every month showed positives. So, but all those values are less. For each month, it's less than what it had been, the negative value in the Northern Hemisphere. So next. Okay, because the Antarctic was not operating the way people thought it would, everybody, the general tendency was to think that because of global warming, ice coverage would reduce. That certainly happened in the Arctic. And in the Arctic, there are all sorts of changes in the system that are all very coherent. The sea ice is reducing, the glacial ice is reducing, permafrost is melting, the temperatures are rising. You know, there's this coherent picture. In the Antarctic case, it was more surprising that the sea ice, at least up until 2014, overall was increasing. So people wanted to look at it in more detail. And when you look at these different regions, one region that stands out is the Bellingshausen-Amundsen Seas, in terms of that one has acted more like the Arctic with significant sea ice decreases, whereas the other regions had increases. And people have tried to explain why the Antarctic ice was increasing. And there were lots of studies done. Some related it to things like the El Nino Southern Oscillation. Others related it to the ozone hole. Others related it to a low pressure system in the Amundsen Sea region. And so there were others related it to the melt of the land ice, bringing very cold water into the ocean, surrounding oceans. So there were lots of reasons. Now with the sea ice decreasing for the past 4 years, we actually have a nice added data set to try to test out the various theories that were made before. So a lot of people are working on that, trying to figure out exactly why the Antarctic ice was increasing and why it's decreasing so much now. So next. So I also look at the global situation, and that's partly because some people, especially in social media, were saying, well, the Antarctic sea ice is increasing, so that kind of cancels out the fact that the Arctic sea ice is decreasing, but it doesn't. It doesn't cancel it out at all, because the decreases in the Arctic were so much more than the increases in the Antarctic, even when the Antarctic was still increasing. So, so I combined the two to get the global record. And this plot shows the monthly averages for the global record. And a kind of neat factor here for those of us living in the Northern Hemisphere, when we always think of February as wintertime. Well, when you look at the global picture of sea ice, the minimum sea ice coverage actually comes in February. And the right-hand picture here explains that essentially. And it's basically because the Antarctic is so much, the amplitude of the Antarctic seasonal cycle is so much greater that its minimum in February kind of dominates. So even though the Arctic has a very high amount in February, when you add the two curves together, you get the top curve there, the global picture, and it does show a minimum in February. The maximum is more variable. Sometimes it's in October, sometimes it's in November, and once in a while it's not in either of those 2 months, and it can be way earlier. But that sort of shows the basic global picture. And then next. This shows the trends for the global picture. And the trends for the global picture do show the downward trend, which those of us in the sea ice community knew they would show a downward trend, since the downward values for the Arctic were exceeding the magnitudes of the upward trends in the Antarctic. But this just plots it out so that it's real clear what the downward trend is, and it's roughly 30,000 square kilometers of ice lost globally each year. And this ice, this is just the aerial coverage of the ice. It's got nothing to do with how thick the ice is. It's just the aerial coverage. And if we update that global trend to the end of last year, in other words, add 4 more years on, then the updated value is a much stronger negative trend, which is 43,400 square kilometers a year. And that's because the Arctic has continued to decrease and the Antarctic has plummeted in the past 4 years. So the trend is now much higher on the global level than it had been for these pictures. So next. So this then shows the trends month by month for the global situation. And like in the Arctic, every single month has a negative trend, but May now is very close to 0 in terms of the global picture, but it's still all negative, but not as negative as the Antarctic case. And when this one is updated through the end of last year, the highest magnitude continues to be September. So highest magnitude means lowest point here, since these are all negative values. So it continues to be in September, but now the updated value is 73,000 square kilometers a year. So next. This is my summary slide, and basically what I've tried to show in this talk is that sea ice spreads over vast areas, and it has important effects on the rest of the climate system through things like reflecting solar radiation and hindering the exchanges of heat, mass, and momentum between the ocean and the atmosphere. The sea ice, because of its vast area, would be very, very hard to collect a good data record of without satellites. And satellites have proven to be extremely good in terms of giving us a record of the extent of and the distribution of the sea ice cover. Now, I haven't shown any results regarding the thickness of the sea ice cover, but there is a satellite up now that was launched in September, the IceSat-2 satellite. It's a follow-on from a satellite that had been launched back in 2003 and lasted for several years and got a record for several years. Its central purpose is to measure the ice sheets, so the land ice rather than the sea ice, but it also is used to measure sea ice thickness, and it does it by using a laser. So it is not a passive instrument, it's an active instrument, sends a laser beam down, the laser beam comes back to the satellite, and you can tell where the surface of the land of the ice is by how fast the photons from the laser beam get back to the satellite. Now, this requires very precise measurements because you need to know exactly where your satellite is, and these photons are going at the speed of light, so they are coming back really quick. So it requires a lot of technology, and that's why the technology for the ice thickness measurements came a couple of decades later than the technology for the extent of the ice. But eventually we'll have a good record of sea ice thickness, either from the laser altimeter, or the Europeans have a radar altimeter in orbit. So then the satellite data have shown prominent changes in the sea ice coverage since the continuous record began in the late 1970s. We did have satellite record earlier than that, but it wasn't continuous with the rest of the record. So over the period from 1979 on, the Arctic sea ice has decreased significantly, and that's true for every month of the year, every season. The Antarctic sea ice up until 2014 had increased. The trend still shows an increase, but it's not as strong now because in the last 4 years, this Antarctic sea ice has decreased. And globally, the sea ice has decreased, and that's true also in all 4 months. And a lot of work is going on to try to explain the sea ice changes, and modeling studies like the one that I showed that was pioneered by David Rind. These studies provide a great additional tool for trying to understand the sea ice coverage and trying to project into the future. And I think Doug is going to probably give us a lot more detail on some of these other aspects. Thank you. Yeah, this simply gives the acknowledgements and also references for where you can find some of this information, including the David Rind et al. Paper.
Claire, thanks very much for that extremely clear talk. Very, very lucid.
Thank you, David.
I have two quick questions, quick for me to ask at any rate. Somewhat speculative in one case. The first is, there is the perception in some portions of the modeling community that climate models, of which there are many, have underestimated the change in sea ice as the climate has warmed. What is your perception about that?
Well, a really good plot on that is a paper Julian Strove did back roughly 10 years ago by now. And in that case, she showed plots from quite a few models, all of which were showing that the Arctic ice would decrease, but none of them showing quite as strong a decrease as what actually happened. Now, okay, so it looks like at least up until that point when Julian's paper came out, the models were underestimating the decreases in the Arctic ice, but that was just the Arctic ice, because many of the models were predicting decreases in the Antarctic ice, and that wasn't happening at all up until that point. So, and there's still clearly a lot of work to be done on both the observational side and the modeling side. But in terms of the modeling, clearly it's not perfect. It's actually never going to be perfect because the Earth system is far, far, far more detailed and complicated than, I mean, we can't put into our models every single little molecule. That is, you've got to have some approximations in there. So, but yes, they were underestimating at least up until Julian's paper.
Thank you. And the second question, which is somewhat speculative, is do you think that in the Northern Hemisphere in particular, that the sea ice trend is likely to become nonlinear? And the reason people have speculated about that is that, as you mentioned, in addition to sea ice cover decreasing, sea ice thickness may start decreasing or is decreasing. And as it gets thinner, it gets more easily removable. So that would imply that the trends we've seen so far might accelerate. What do you think about that?
Well, the decreases in the Arctic have accelerated. So definitely, if you look at the plots of the Arctic sea ice, like the monthly deviation plots, you'll see they did accelerate. However, there is a lot of interannual variability, so that, well, 2007 was a really extreme case in terms of the ice plummeted in September way below it had ever been before in terms of what we've seen from the satellite record. And everybody involved with the satellite sea ice studies is just shocked by how much it plummeted that year. And that's a year when soon after people started saying we might see an ice-free Arctic a whole lot sooner than had been predicted up until then. Some people were even saying we might see it within a decade. Now, a decade has gone by now and we haven't seen it, so those predictions were wrong. But it rebounded. It rebounded a bit over the next couple of years. But then in 2012, it went down even further than it had gone in 2007. So, but then it's rebounded. So the 2012 remains the lowest value that we've seen in the satellite record. And so it's clearly got a lot of interannual variability in it. It's clearly not linear in terms of not being a straight line. But the linear trends, I think, are still valuable to look at. Maybe less so in the Antarctic than in the Arctic, but it's. I would agree that it's not linear, but the linear least squares fits are still numbers that are, you know, worth looking at anyway.
Thanks very much.
Okay, thank you. Good questions.